Hi, my name's Leanna, and this is a screencast for the air rocket activity. So an air rocket is shot straight up into the air, and it falls back to the ground where it was launched. The rocket is launched with a low, medium, high, and a super cap. As you can see here, when we actually did the experiment, it took 4 seconds for the total time at the low cap and 4.5 seconds medium, and you can see the rest. So here's a diagram of all 4 rocket launches. The black being the super launch, blue high launch, red medium launch, and green low launch. So if you look at the the low launch, you'll see that right around here where the mouse is, you'll see that that's where the velocity is 0. That was the maximum height, and it was about 2 seconds here. And you'll see that I drew for the velocity graph at 2 seconds. Over here, that's where the velocity crosses the x-axis, meaning that the rocket switched directions at that point, so it had to be at the top of its height. And we can take a closer look at the velocity graph. You'll see here the velocity for the low launch, well, for all these launches. It increases its speed going in a positive direction because I signaled going up into the air as positive and going down as negative. So here in the velocity time graph, you'll see that the velocity was increasing, and then it started to decrease, but the direction still hadn't changed yet until around 2 seconds for the low launch. It changed directions. The rocket was coming down, and it increased its speed at a much faster rate. Well, actually, that's not true. Its speed increased even more compared to its initial speed over here when it was going in a positive direction. And here's the acceleration time graph that corresponds to each of these launches. We'll look at the low launch again, the green, and I'm really just assuming that we're using 10 meters per second squared as our acceleration for the low launch, but I think there's more than just gravity affecting the acceleration. So this is probably incorrect. Unless, okay, so after the rocket reaches its maximum height, then the only force that would be acting on it would be gravity. So everything below the x-axis here should be 10 meters, negative 10 meters per second squared as the acceleration. So instead of these 4 separate lines, you would see one whole line going across for each of these launches. But the acceleration, the initial acceleration, that would be different because each launch had a different amount of power. That's why there's different caps. And that's why some rockets were launched higher into the air and took longer to come down. So I don't think that I have any way of finding the initial acceleration for any of these rockets, but we know that after any of the rockets had changed directions, they had reached their maximum height. We know that the acceleration after that point in time would be negative 10 meters per second squared. So let's just say that, okay, so what was the change in velocity of the rocket? Well, change in velocity is, you can find that by calculating the area under the acceleration graph. So if we look at the green launch at around, this actually is not 2 seconds right here, this is 1 second. From 1 second to 4 seconds, the acceleration is negative 10 meters per second. So we calculate the area of that rectangle here. 10 minus 30 meters per second. Because here, at 3 seconds, no, I'm sorry, this isn't at 3 seconds. This is the total time, which, actually, let's just make believe that we're only calculating for after the rocket had reached its maximum height. So we'd only be looking at this area, not here. And if we were doing that, then the total change in velocity after the rocket had reached its maximum point would be negative 30 meters per second, because it traveled for a total time of 3 seconds, and this is after it had switched directions. And its acceleration times time. And, right, so 3 seconds times negative 10 meters per second squared. And that would give you the change in velocity, which would be negative 30 meters per second. I'll just write that here. Acceleration equals negative 30 meters per second. Oh, I'm sorry. That is not acceleration. That is the change in velocity. Change in velocity equals 30 meters per second. How fast was the rocket traveling when it was launched? That is the initial velocity. And here we'll look at this equation. The final velocity equals the initial velocity plus the change in velocity. And if we don't know the initial velocity, but we know the final velocity, which was here, well, that's a change in velocity. Assuming that we start from an initial velocity of 0 meters per second, then we would go ahead and go 0 minus 30 meters per second, and we would find the final velocity. But we're not, I'm actually not sure what the worksheet is doing, like if we're supposed to be calculating from after the rocket was changing direction at its maximum height, at its peak. Yeah, so this is confusing Mr. J. And the speed when the rocket was launched would be different from the speed before the rocket hit the ground, because if you look at our velocity time graph, the velocity after the rocket comes down, it reaches a much further down velocity, like its speed is greater. You'll see it's further down the y-axis than it is when it was going up. It just reaches this little point. But when it goes down, whee, right there. How do we find our maximum height? Oh, let's look. Our maximum height here, at this point, velocity would be equal to 0. So the maximum height velocity was 0 meters per second, which means at the max height there was no acceleration. This would go for all the rockets, and the total distance that the rocket traveled would be the change in position. Well, that's not true. Change in position would be displacement. But first, let's look at the distance. So how far away from the initial position did the rocket land? So total distance does not take in change in direction. So our final position was 0 because the rocket landed in the same spot. So final position and end position are 0. 0 minus 0 is 0. No distance. Scratch that. That was the displacement. That was my bad. The displacement is that. The final position minus the initial position. Distance actually measures how far you traveled. Like if you traveled 60 meters in one direction and then 20 meters back, your total distance would be 80, but your displacement would be 40 meters. Um, so here we go, the displacement for the rocket, any of the rockets is 0 because they landed and started in the same position. And then for distance, that's another story. It depends on how long it took for them to, or not how long, but how far in the air, what their maximum height was, and then add the distance from maximum height to position again to the initial position, and there you would have your distance. So the distance of the rocket and the displacement are different due to the initial and ending positions being the same, but the rocket did move in the air, so it did travel some distance. Thanks for watching this screencast. I'm Leanna from Period 5. And again, I'm sorry, Mr. Day. This was really confusing, and I think I was absent for some of the days, but for the first day that this was assigned. Okay, so I tried. Bye!